Welcome, everyone. I'm excited to be joined today by Anthony Caterini, a senior machine learning scientist at Layer 6, who heads up the algo trading team, providing models with real-time inference capabilities in both equities and fixed income. He recently co-authored a research paper exposing the flaws of generative model evaluation metrics, in which Prolific was cited as being a resource for gathering human data, and that project will be the main topic for our discussion today, speaking to the research that was performed, the outcome, and how Prolific was able to help. Anthony, thank you so much for joining me today. Anything to add there with regards to your background that I maybe missed?
No, I guess, so the projects we're working on now, you highlighted equities. So we're also working on now chatbots as well, like everyone. So we're trying to give a chatbot to the equities team. And we have a model running in production as well that trades bonds. So that's kind of cool to actually watch it trade stuff.
Yeah, interesting.
That's
very exciting.
Yeah, more to kind of the applied side of things. But this is more so, I guess, for Layer 6 as well, to give a bit more background there. So we have two kind of mandates as a research scientist. So one of the mandates is like more the applied side, and then the other mandate is more the research side. So we generally research in interesting topics, try to focus things more towards like what the bank is interested in, but we still have freedom to do other stuff like this project that we did with Prolific.
Nice. That's cool. It's good to have that type of flexibility, I suppose. I guess jumping into the project, for the research paper that you co-authored, do you mind giving an overview of the research and I suppose the goal that you were looking to achieve?
Yeah, so maybe not to get into too much detail, but kind of overall what the project was trying to do is we were interested in evaluating the quality of generative models, specifically for images. So in the vision domain, there's been a lot of buzz about diffusion models. So one of the very popular things to do these days, and actually my wife was literally doing this yesterday, is to take some text and turn this into an image, right? A very popular use case. And a lot of those models are backed by diffusion models. So diffusion models are a particular class of models that have essentially shown really good generation capabilities. They're like the next generation of image generation models. The previous generation of image generation models was mostly generative adversarial networks, or GANs. So these were more popular. They kind of came up about 10 years ago. Then they were kind of the standard for image generation. So with this background, we have GANs and diffusion models, right? And the whole point of this research was we started to notice kind of a difference between what humans perceive as high quality images and what people are actually using to create their images. And we started to notice a divergence between that and the metrics that were reported for image quality. So once we saw this kind of discrepancy between what was actually being used and what was being scored highly in research, we thought, hey, this suggests that there's a problem with the metrics that we're using to assess image quality. So should I get into more of the background of the metrics, or
yeah, if you'd like, that certainly would be interesting.
Yeah, sure. Yeah, so the metrics that people had been using or were quite popular were essentially based on kind of like some kind of distance between like real images that you had and the generated images that you created. So you would measure this distance between, summary statistics of the images, like the average of the images and kind of the variance of the images. You would measure this in some kind of embedding space. So you wouldn't measure it right on pixel space. Like you wouldn't just compare the images directly. What you would do is you take these images, you'd embed them, in some kind, using some kind of maybe very complicated model, and you get some embeddings, and then you compare essentially the statistics of those embeddings. And so that was how things were being done. And the particular embedding model that was being used was in fact very similar to the architectures that were being used in the GAN models that were kind of most popular. So effectively what we saw happening was that GAN models were getting scored highly on the metrics, or being scored well on the metrics that people were using, but were not being actually used to generate images in practice. People were using diffusion models to generate images in practice. So what this told us was that, hey, there's something wrong here. We need to investigate. And all of these metrics are being computed offline. Like, people are not involved in actually scoring these images generally, right? So when you write a research paper, let's say you write a new technique for image generation, a typical thing that you would do is you would compute one of these metrics. The most popular one was FID. So you would compute this FID metric, which is how I described. You take the images, you embed them, you compare the summary statistics, and there's no human in the loop. You just do this all offline. You calculate your metric, you report good performance on this metric, and then that's kind of that's it. That's like all you did.
Yeah.
Right. And so we thought, hey, there's something wrong here, so let's investigate. And then the whole point, kind of like long and short of what we were trying to do, is essentially get humans involved to see if people could validate whether or not our hypothesis was correct, that this metric was deficient and perhaps favoring GANs because the architectures were sort of similar in how these how the evaluator was working versus how the model was working, which perhaps created an unfair bias that made GANs look better on these metrics than they actually were.
Gotcha. That makes sense. Yeah. Do you mind getting into the tasks that you were having the annotators perform?
Yeah, sure. So I guess maybe to give a little bit of background on what we actually had them do. So we figured, hey, we need actually human evaluators to assess whether these generative models are good or not. And so we thought, hey, let's use Prolific. It has high quality data. It's known to, it has a large group of people that can essentially answer questions for us. And so the task that we actually had people do on Prolific was, we had what's called a two choice force test. I might have the ordering of words wrong, but essentially you have how we assess the quality of generative models. The whole tenet is that if a generative model is good, you cannot tell if it's a real image or a generated image, right? So the whole idea of our evaluation was ask people whether or not an image is real. And how we did that was we would provide two images for a single trial. We would provide two images. One is real, one is fake. And we would ask people which one is the real one. Essentially, the task was, so to give a bit of background on what the task, what kind of we were trying to answer with the task, our whole idea is that a good generative model, you shouldn't be able to tell if an image is real or fake from it. You should not be able to say like, oh, I know that this was generated from a model as opposed to a real image. And so to that end, we performed this test that was it was called a two alternative forced choice test. It's well back in psychology. I'm not an expert in psychology, but one of the other team members was. And so what we decided was that essentially we will show images from either the real data or generated data. And we ask people to tell us whether or not they think it's real, right? And we do this. So we started off with a a training session, more or less, where let's say we pick one model. What we do is first we show the participant 20 images, well, one at a time. We'll show them an image for a total of 20, and we have them say whether it's real or fake, and then they get feedback whether it was real or fake. So there's like this little training period, and then there's this testing period where we have a total of 100 images, and half of them are real and half of them are fake, and we show the participant one by one in random order images, ask them if the images are real, and we don't give any feedback this time. It just goes to the next image. And essentially what we do, so that's one model and one participant. We will ask, we'll do the same task for a single model. We'll do this for a bunch of participants. And then we'll do the same thing, the same whole overall thing for a bunch of different models. So the idea being that we want a sense of how much people were fooled by a particular model. And then if you're fooled more, that means that the generative model is of higher quality.
How many different models did you get outputs from?
I believe there were 13 models.
Okay.
I think it says in the abstract. Something like roughly 10, but more than 10.
Yeah.
Something around 13 models.
Cool.
And they were different types. So we had GAN models, we had diffusion models, both major model types that I was talking about before. And I believe we also had some other older types of models. There was like perhaps a VAE-based model, which is kind of not as good of a generator. There was also a transformer-based model, which were not bad. But yeah, the focus was mainly on GANs and diffusions because those were kind of the main model types that we were trying to differentiate between for our research question.
Yeah. And were the image pairings random, one generated, one real, or were they paired because they were similar in some way, or how was that decided or set up?
So there was actually so when the people actually receive when we ask them the question, it's just one image at a time, right? So but the model itself was trained on the data set that, I guess, yeah, when you say like pairing in terms of like we have to combine data sets to then show them individually to the end user. The models were actually generally trained on that data set that they're being shown to the user. So let's say we had a model for some data set. Popular data set is called ImageNet. It's one of the more popular computer vision data sets. We would show images from ImageNet, and we would also show images from a model that was trained on ImageNet, a model trained to generate ImageNet images. So that's how there's kind of like a natural pairing there.
Yeah. Okay. I guess what were the results and the findings? Like I'm curious to hear what you all learned and sort of what the results of the studies were.
Yeah. So that's kind of the meat of the research, the most interesting thing. So I was saying that we have bunch of different models for generation, and we also have a bunch of different data sets that we looked at. We were mostly focused on ImageNet because that's kind of the biggest one that people do for generation. So the long and short of it is we found that the existing metrics do not correlate well with human perception of quality of generated image. And this is kind of totally agreeing with our research hypothesis. Essentially what it showed is that GANs, GAN-based models don't fool humans as much as diffusion-based models, even if they get higher scores on this FID metric, which I was discussing earlier. And you can, it's quite borne out in the results. So another thing that we noticed which we thought was pretty cool. So remember how I was saying on the metric, you take like generated images and real images, you put them through some kind of encoder or embedding model, and you get some embeddings and you compare the statistics. Well, the choice of the embedding model matters a lot. So previously we argued that the embedding model that was being used mainly in the literature was almost like had the same structure as a GAN. And so it was unfavorably giving GANs good scores on its metric. But if we took a different embedding model, so that embedding model is called Inception. I mean, the names don't really matter, but that's the I in the FID. If instead we choose a different embedding model, so there are a lot of image embedding models that have come out recently. And so if we choose a different embedding model, we get different results for this kind of embed and then compare metric. And we found that a different model called Dino V2, just another sort of, it's like a more advanced image embedding model. It's more advanced than the Inception network from before. We found that this actually correlates a lot better with human perception. And so the recommendation of our paper, I mean, we had a lot of other experiments in there too. We looked at things like memorization, diversity of images, whatnot. But the only thing we actually used human participants for was the fidelity of images, like how good is the generative model at producing realistic images. The recommendation from the paper overall was use this Dino V2 in your kind of metrics instead of using the existing FID.
Got it. So it sounds like part of it lined up with expectations, and maybe the latter half that you explained was not what you were expecting going into the study, correct?
So yes and no. So we kind of thought that the embedding model that you used was important, but we didn't know which one was going to be like the one, or we didn't know if one was going to align more with human preferences. There's no kind of guarantee, like it's possible that a new embedding model would work on scoring some models, but not others. Like it wasn't clear that we would have like a really obvious winner among embedding models. So that was a nice outcome. And actually, so that's been kind of our headline recommendation. And I think it's starting to get picked up a bit more in the literature. So for example, but people from research papers from NVIDIA are citing this, saying like, oh, we're actually using this metric.
Got it. Okay, cool. I guess shifting gears slightly, unless there's anything more like from the findings that you wanted to touch on, I guess from a prolific usage perspective, like I'm curious why you chose to use prolific in the first place for this particular project.
Yeah, so we have kind of there's a few reasons for that. So one of the major reasons is that, so I talked about how somebody in our team, his name is Eric Taylor. He's more of a psychology expert. I believe he has a PhD in psychology. He actually knew about prolific from his graduate studies. So he was the one who initially recommended that we use prolific if we want to get a large base of human evaluators to draw from. So he was saying, yeah, we should use prolific. And also, I was like, yeah, absolutely. So it turns out my wife works at Prolific and was one of the early employees. So I've known about Prolific for a long time. But so people, I think, just assume that I was pushing for the use of Prolific, but actually it wasn't even me. It was somebody else had already used it. And this was fairly early on. Like we were talking about using Prolific since like early 2021. And he had already used it. And now Prolific has grown to be a fair bit larger. So that's a couple of the reasons. So overall, at the time, it was kind of like mostly Prolific or use something like Mechanical Turk from Amazon. But my understanding of Mechanical Turk is that it has more issues with non-human users, bots mainly. I understand that Prolific has a lot more identity checking. I remember when my wife early on had to deal with some support tickets. It was often like people saying, "Oh, I'm a real user," but it was like their driver's license didn't make sense, or it wasn't uploaded, or they had no proper identification. Like, so there's actually a lot of steps in place, seemingly, to get high quality data and make sure that people are actually people. Um, so personally, I have a lot of confidence in the human evaluation from Prolific. So yeah, that's kind of why we chose to go with you guys.
That makes sense. And just no conflict of interest at all.
Yeah.
So to clear that up.
Yeah, I wasn't the one who was pushing it forward. So I was just like, oh yeah, I hopped on the bandwagon when it was already being said that we should use it.
Yeah, makes sense. Do you recall how you used Prolific? Like, were there specific audiences that you were targeting? Was there any sort of like filtering that you were doing? Like, how was Prolific being used to be able to source the right audience, I suppose, is the question. Was there anything in particular that Prolific was able to help with that maybe someone like mturk or other competitors, other suppliers wouldn't have been able to do to the level of quality that you saw with Prolific?
Yeah, so I guess I already discussed about the data quality issues or concerns that we would have with somebody like mturk. Knowing the process of verification at Prolific, it gave me more confidence in that the data would actually be good. Another thing, Prolific was actually quite responsive in terms of if we had any issues from a customer service perspective. So that was quite nice. I don't, yeah, I wish I had more to say. I know that Prolific had an API that could be, you can kind of put some of your own code in to then share with the participants so that your test could be run.
Yeah, no, that's great. Cool. I mean, I appreciate the sort of the overview of the study itself. Not to move on beyond this work that you've done in this space, but I'm curious, like, what's next for you, right? If you have any exciting projects that you have coming up that you're able to speak to or share about it all, like, it's always interesting to hear sort of like, how people are continuing to work in this AI space.
Yeah. So not me personally, but one of my colleagues who was on this paper, his name is Jesse. He actually completed another paper that was just recently published at ICML 2024 that again used Prolific for some human experiments. The whole idea there was that so you could, I'm not an expert on that paper, but the whole idea there was that you could essentially prompt people with, so let's say you have a kind of a classification question that's challenging. Like whether an image is kind of unclear, whether it's like, I don't know, a bird or the bat, maybe like something flying in the air you can't really see. There's all kinds of examples like that. But anyway, you can actually essentially prompt, if you prompt a human smartly on like giving them a particular set of images and saying like what they are, if you kind of are a bit smarter than just doing this randomly, if you use this some sort of particular statistical technique, then you can, he showed there, him and his team, they showed that you can improve the performance of people on classification tasks.
Yeah.
So this is perhaps useful if you have human in the loop for like, if think from the bank's perspective for a minute, if we have a human in the loop for credit scoring or for mortgage applications, you can think like, if we give the person, the evaluator, some specific examples of previous credit applications or previous mortgage applications, not overwhelming them, like trying to keep the set of examples we give them as small as possible, but kind of deliver them these examples in a smart way, then they might be able to make a better decision. So that was one exciting work that still used Prolific. For me in particular, I don't have anything upcoming in the pipeline that is actually using Prolific, but it could at some point. For me, what I'm working on right now from a research perspective is trying to build tabular foundation models. So tabular data is a particular data type that really is the most pervasive in industrial applications. Just think of really any table of data that you would have, like all sorts of stuff can be written as tabular data. Pretty much any data science problem can be converted into a tabular data problem, I would think. But foundation models for that have lagged far behind, as opposed to foundation models for, say, language, which of course ChatGPT, there's an example of that. There's also foundation models for vision. And we use foundation models for vision for this previous project on embedding images and that, calculating their distance. Those relied a lot on foundation models for images. So these things exist, but tabular foundation models are way behind. So what we're working on is trying to improve the space there.
Yeah, that's interesting. Cool. Well, Anthony, it's been great speaking with you. Really appreciate the time today. Looking forward to following your work and seeing what else you do in the AI space. And appreciate the time from everyone watching this.
Yeah, great. Thank you as well.